Welcome to a lesson with Dr. Powell. Let's take a look at an example of diagonalizing a matrix. So we take this matrix, we have x times the identity minus it, so we have like x minus the um, uh, matrix, okay, where x is down the diagonal, um, and so we end up getting this, um, and we can use a cofactor expansion down a column or a row. We have this times the determinant with kitty corner to it. We get this factors very nicely. Now this will only be diagonalizable if the minimal polynomial doesn't have any square factors in it. If it looks something like this. If we had a square factor, then the problem is what we would have. We would have something like x minus 1 squared in there, and there will be vectors in there that when we're trying to kind of split it up into linearly independent parts to find linearly independent vectors, the x minus 1 squared part wouldn't actually give us everything we needed. We wouldn't have dimension 1. In fact, down the diagonal, you wouldn't have anything right here. It would just be on what's on the bottom. And just kind of building this up, we have to like multiply x minus 1 times x minus 3 before and look at the range of that to get the eigenspace, what has just degree x minus 1 as the minimal polynomial. And by that time, we'd have dimension 1. X minus 3, we're looking at the range of this, which would give us uh, the range of that, which would be a dimension 1 as well. So we wouldn't have enough dimensions. You can work out the particulars, but there wouldn't be enough dimensions to actually make it to have 3 linearly independent vectors here in that case. But just the general rule is, beside all the commentary, is you just need to make sure that that's the minimal polynomial right there. So if you multiply these two matrices together, so this matrix minus 1 down the diagonal times this matrix minus 3 down the diagonal, you should get 0. And if you did it, then it is diagonalizable. That's good. But we can also just start by looking at the range of things. Look at the range of x minus 1. And we end up getting this, all right? X minus 3 makes this 0. Okay. And then if you look at, okay, so that's the range of x minus 1. And notice that x minus 3 actually makes all of that 0. The range of x minus 1 is actually one-dimensional here. That's okay. So meaning that multiplication by x minus 3, it just has one more dimension to go down, which it must go down by one dimension here because this is not an invertible matrix. So as we're taking a look at this, and we have to get to 0 when we multiply these out. So it looks like this is the minimal polynomial right here, since just one multiplication by x minus 1 actually takes us down 2 dimensions. That's kind of nice. So we can actually see that just by computing that. But if we really didn't see that, I guess what we could do is we could just multiply this out and see what it is. And so it's basically this matrix times that one, and we get the 0 matrix. And you can actually just check it. That matrix times that man is the 0 matrix, so we're good there. Okay, but nonetheless, we can find the range of this by just subtracting 1 down the diagonal. We get that matrix, and we look at the columns, and it looks like they're both multiples of that guy. So that's good. So that's the one eigen. This is the one eigen. We can say basis. It's a basis vector, and it only has one thing in it. It's an eigenvector because it's in the eigenspace for x minus 3, because x minus 3 is going to make it 0. So that means that matrix X acts like 3 when we multiply by it. So in a diagonal fashion, that means it's going to act like 3 but we're going to pull it back to the first standard basis vector. We want this whole combination right here to be the same thing as multiplying by 3 to that standard basis vector. So first we got to take that first standard basis vector 1, 0, 0 to 0, negative 1, 1, and we know that this guy is going to act as multiplication by 3 on it. And then we'll just reverse what we've done here over here to send us back to standard basis vectors. since this will send us to 3 times the standard basis vector coming out here. And then if we just invert what was done here, we'll send that standard basis vector, we'll send this vector, right? 0, -1, 1 back to the standard basis vector, but with the 3 carrying through. So we'll end up getting that. That's kind of the idea. So we'll kind of build this matrix as we go here. So this with an eigen value of 3. Now here we actually get 2 things for, so the eigenspace for x minus 1 actually has dimension 2. So we can write down a 1 and a 1 for that eigenvalue, and associated with each of those ones, we just put down what we see here, -2, 0, 0, and 0, -3, 1. Now, how did we find these? By simply computing this range right here and noticing what spans it, right? That span, these two, this is just a repeat of that one. So, but these are linearly independent. So that works. So we actually get this much done so far. Now, the only other thing to do now is to compute the inverse matrix of this guy and put it right